do the recording.
Sure.
Please go ahead. Yeah.
Okay, so Liliana, if you want to share your screen, we can go ahead and get started.
Can you see my
screen? So I see your slides, I see your mouse, so
Perfect.
Everything looks good. For everyone else, we're happy to have Liliana here, talking to us very late at night in Lisbon, coming here to talk about jet quenching. So go ahead, take it away whenever you're ready.
Okay, so thanks a lot for the invitation and for the opportunity to talk about this topic. So I'm going to try to motivate a little bit how can we use jet substructure to actually classify in medium and to select in medium jets. So as just a short introduction, as we know, jet quenching is a really important step to define the presence and to establish the presence of a quark-gluon plasma. And in fact, it's one of our standard candles and also one of our problems when moving to lighter systems, in which we see a lot of jet quenching, a lot of quark-gluon plasma signatures, but not the presence of energy loss effects. And historically, jet quenching suffered a lot of, people had to address this topic, and the amount of developments that this field has suffered was enormous, because we went from a situation in which we only care about the leading particle, as was the first collisions at RIC, to a situation in which we are able to actually reconstruct the full jets and the full kinematics and all the interactions that happen during the propagation of all these particles across the medium. Of course, that's aligned with all these theory developments. This has to be accompanied by some very severe efforts on the experimental side to actually control the background, because we don't have only the hard signature of the jets. Here, for instance, is an example of one of the most striking events of jet quenching, in which we have the almost complete disappearance of the DOA site when dye jets are produced. But we have to deal also with the large background and to handle all the challenge to reconstruct jets in a large fluctuating background. Currently, I think that this is already quite well understood. And now, of course, we are moving towards larger and larger radius jets, which pose new experimental challenges that need to be also handled. Now, of course, that with all this, the first things that we could aim was actually towards assessing the global jet properties. And this means that, for instance, one of the first observations that we did was actually to measure the jet spectrum and to make, of course, the ratio with respect to proton-proton. And this was one of the most direct observables and one of the first ones as well to come out from lead-lead collisions. And of course, that this was very useful and it is currently very useful to actually try to tune the current jet quenching Monte Carlos and models. But the problem is that all these observations now, when we look for the jet RAA, they are done in terms of a fixed beam, a fixed PT beam of the jet. And so this means that when we look to the given PT beam, and we compare the proton-proton reference to our lead-lead yield, this means that most of these jets, because of jet quenching effects, actually, some of these jets will migrate out of the beam and will come out of our sample. And it's true that we have some feeding effects, but since the spectrum is so steeply falling, at the end we are always dominated by jets in this given sample, in jets that are typically narrow and that typically underwent less jet quenching effects, which means that this is the known selection bias, in which we are constantly, every time that we want to check jets out in a given PT, we are always selecting or ending up with the selection of jets that are weakly modified. And this conclusion was, it has been some years that we know this, and most curiously, this was actually found both in strong or weakly coupling approaches. And so quite a few years, a couple of years before, there was this idea from these authors here that, okay, let's, instead of comparing jets that has exactly the same final states transfer momentum, how about we compare jets that have the same initial transfer momentum? And so instead of having the ratio of the lead-lead yield to that of the proton-proton yields, let's do the ratio in terms of the cross-section. Of course, that it was not exactly this proposal that they put forward, was something that they called the quantiles. And the quantiles, because the procedure was in fact to do a quantile of the cross-section and use this as one proxy for the initial PT of my jet. And in this case, this means that I can compare exactly jets that had the same initial PT, and then I can control exactly what kind of energy loss effects these jets went. And as you can see here, the predictions, for instance, for the equivalent of the energy loss when using the RAI for Z plus jets or die jets is quite different. While using the quantile, these two distributions actually match. And in the Z jet, we have a perfect channel to study energy loss because it's auto-calibrated. Of course, this idea works very nicely, but it has one disadvantage, that is, this works very well when we have a monotonic energy loss function. But given that we could also have energy loss fluctuations, and we know these are also important to understand our phenomenon, this unfortunately is not so far very easy to implement. So up to now, the best, let's say, probe of energy loss, our golden channel, remains to be the boson plus jet, in which we have the boson on one side that is a good proxy for the amount for the initial energy of my jet when it is produced. And this means that when I afterwards detect my jet, I always have a good handle on the total amount of the total amount of energy that the jet has lost. And this means that I can control exactly what kind of jets I'm looking at. So if they are strongly quenched or weakly quenched, depending on the energy asymmetry that is between these two objects. And so I can start looking now inside of my jets, and I can start looking to the jet fragmentation functions, to the jet radial profile, and I can even play with the fact that I can now make comparisons with respect to the PT of the jet, the final momentum of a jet, and this would give me relative information of the PT smearing inside of my jet. Or I can look even for the PT of my boson, that it's a proxy of the initial energy of my jet, and this would give information, absolute differences with respect to the initial energy loss process. Of course, that although this is a golden channel, we know that it has some limited statistics. So when looking for now the whole collection of effects that the jet can undergo when traveling through the medium, we see that there are a lot of effects playing a role here. We have on top of the Parton shower, we have additional medium-induced radiation. We have the interaction with the backgrounds, with the quark-gluon plasma, that will induce extra radiation, so what we call the medium recoils, and will be correlated with the incoming direction of my Parton. And we have, of course, a very fast expanding medium that, of course, will control in somehow also the magnitude of all these effects, depending on which stage my Parton shower is at the moment. So we have several unknowns, and it turns out that at the end of the day, we of course are able to measure average quantities, but we want now to go one step further and try to understand exactly how can we control better our understanding on all these phenomena. And if we want to understand all these phenomena independently, we also need a sample that in which we can play more with the effects of all these things. So we need some sort of classification tool. And this is where, let's say, when we talk about classification tools, the first thing that comes to our mind is, of course, deep learning techniques that now currently are much more used and easy to apply, let's say. So as a first simple idea, let's look for low-level jet information. And what I mean for low-level jet information is just look at the colorimetric image of the jet. And we ask ourselves the simple question, if a neural network can in fact be trained on a jet-by-jet images and be used as a discriminant. So for these things, for instance, we use Joule as our Monte Carlo reference. And as you can see, this is the colorimetric image that we reconstruct from Joule. This is an example of the vacuum simulation without medium effects. And this is the simulation that when we turn on the medium effects on top of, so the Parton shower interacting with the medium that in this case is described by a Bjorken model, in which we, for simplifying right now, we don't consider any kind of recalls. And you see here that, okay, this is one event, it doesn't mean anything. And if I look for the average image of my jet, in which I put the log scale on the colorimetric images to enhance the differences, we see that we don't see particularly also any kind of, let's say, difference between these two jet images. But of course that for a neural network, this might actually work, because now if I simply take the average and divide as for the vacuum, taking this as the reference, we see here that we have indeed some sort of information in which we have differences in the PT regions that are occupied by my particles with respect to the vacuum reference. Now, this idea is not new, and the jet images were actually used by these people here in a somehow different way. So what they used was to simulate samples from the strong-weak hybrid model. And because they have full control of the shower, they actually can make the match between the vacuum Parton shower, the hypothetical vacuum Parton shower, before it enters the phase in which medium effects start to take place. So they have full control, jet by jet and event by event, on what is the energy of my hypothetical vacuum jet that they denoted by the subscript I from initial, and the jet after undergoing this energy loss effects. And in their case, they also consider the medium response that is included in the hybrid model. So they make the ratio of the final jet with respect to this proto initial jets, and they take this as the average energy loss that they can, or the energy loss that they can retrieve from the Monte Carlo jet by jet. And as you can see here, this is of course that are again average image of jets. And as we increase in this direction the magnitude of energy loss effects, so this variable psi decreases from 1 to smaller values, we see that the jet image is in fact becoming different. So again, this is a very good hint that perhaps this fit to a neural network can help to create some algorithm that allows to identify jets that were strongly quenched from the jets that were less quenched. In our case, we took a different approach. So in their case, they have hybrids that has medium response. In our case, we used Joule that, despite the fact that has medium response incorporated, we didn't include it in the beginning. And this was because medium response as implemented by Joule is based on perturbative prescriptions. And in order to avoid this this is also the most model-dependent component of this Monte Carlo. So in order to avoid this contamination, we only use Joule without these components. And we feed them exactly these jet images reconstructed from Z plus jet events, and we handle this to a CNN that were trained with 2 channels, so the number of constituents, the multiplicity, and the PT of the jets in 2 ways. One, in which we normalize the differences, we normalize the images, so the only thing that was given as input for the CNN was the jet images that just reflect the relative differences between the 2 samples. And the other in which we also didn't normalize the images, so we just gave them with the absolute values of multiplicity and the PT of the jet. And so we use these 2 as our, let's say, 2 methods that we could test. Here is the output of the deep neural networks. And of course, that's our goal. Here, it becomes the first problem. It appears the first problem because our goal is not to separate the Joule vacuum from the Joule medium reference, but to withdraw the list of, let's say, unquenched jets, the ones that didn't experience so much interactions with the medium from the rest of the sample. And this is our first problem. The second problem is that when we look to this question as disease, this means that our problem is not exactly a binary classification problem. So this kind of approach is also not ideal. But in any case, we can look for the output and try to at least make some sense and try to understand exactly what the neural network is trying to tell us. And let's say that I want some relative contamination from medium and vacuum, but still I want to make sure that I have the maximum discrimination between these 2 samples. So I selected, in the case of the normalized images, the 0.5 as the value of the criteria given by the CNN trained on normalized images, and 0.6 from the training in unnormalized images. But one thing is for sure, it seems that only from these plots that the absolute information given by the number of constituents of the jets and by the PT of the jet is already important to maximize the difference between these two samples. So with this output chosen, we can now look for the class of jets that I want, that the neural network gave me. And the first thing is, let's look first for our reference, which is the spectrum of my Z boson. So from here on, all the plots will go by this color scheme and by these labels here. So orange is always referring to what we call vacuum, and blue is always mentioning what we call medium. The solid lines corresponds to the solid markers, correspond to the reference provided by Monte Carlo, that is Joule vacuum and Joule medium, while the open symbols refer to the outputs that the neural network thinks that it classifies as being vacuum-like, that is below this threshold that I put in the previous images, and what the neural network thinks that it's medium-like, that is with this output above this threshold. So in this case, 0.6 and again 0.7. And the first thing you can see is that the PT of the Z boson in the vacuum or in medium Joule always follow this kind of behavior, because the Z boson is not modified by the medium, but the fact that I'm applying only the criteria to the criteria of the neural network only to the Joule medium sample, this means that now I'm selecting different topology of the jets. So the jets in which the jet didn't undergo much of jet quenching, the neural network hopefully will classify this as vacuum, and will, because of that, will distort the resulting spectrum of Z bosons for the medium sample. And this is exactly what we see here. Despite the differences, both of them are selecting a soft part of the Z boson spectrum. Now, one of the complaints that, of course, people can do with respect to this approach is that jet images are, of course, not much reliable in a heavy ion environment. In fact, I think it was Mateus that told me that they actually tried this already in a list, and it didn't work out. Of course, because the background here it's really large, and the information that we encode here is, of course, blurred by the background contamination. But the other thing that we also tried was, in fact, use Lund planes, and not only the Lund planes, but the sequence in which this information of the Lund planes appear. So we have our jets, we recluster with the Cambridge-Aachen algorithm, and we unclustering this sequence, providing always the sequence of values in this Lund plane. So this is the average Lund plane. Of course, that this is given to a neural network, in this case, a recurrent neural network. And we give exactly this pair of numbers, so the log of the transverse momentum and the log of delta R. And in fact, we tried different variables, but they all yield more or less the similar results. And even we played a little bit also with soft-drop, and it didn't appear to change much the resulting output. Of course, that's the hyperparameters of the neural network were not optimized for this case. So these results are in fact without soft-drop. But as you can see here, this is the output of the neural network trained on the sequence of in the Lund planes. And we see here again, more or less the same behavior as we could see for the unnormalized images. That is a really large difference between what between the medium and the vacuum training samples. And again, we chose here somehow an output that, again, it was arbitrary. We didn't try to fine tune much these parameters to make our selection, but to illustrate more or less what kind of jets are we selecting when using the neural network to provide us an answer. And so let me try to compare now these three setups. So these three neural networks, one that is trained on jet images normalized, what we call normalized jet images, in which we normalize the constituents and the PT of the jet to 1. One that in which we give exactly the same information, but without normalizing. So we give the absolute value of the PT and the number of constituents. And the other one, finally, in which we give the same jet, but afterwards, after reconstructing the jet with Cambridge algorithm and giving exactly the unclustering history to the neural network. And as you can see, again, we see that in this case, we are looking to the boson jet asymmetry. And one thing is for sure is that, again, the neural network is identifying medium-like distributions as being pushed to even lower values of xjz with respect to the Monte Carlo truth. So this means that the medium-like jets as identified by the neural network lost indeed more transverse momentum with respect to the Z boson as compared to the Monte Carlo truth. And this is visible across the three architectures, these two yielding very similar results. And of course, the one in which we don't give the information of the absolute value of the PT and the number of constituents is the one that actually most closely resembles the Monte Carlo truth. But this is the feature that we are not aiming for. So we know that the Monte Carlo truth will have a mixture of these two classes of jets. We tried to understand more what were the features that the jets, that the neural network was selecting. And we look also for the jet mass. Again, we see that the medium-like jets across all the three architectures give a very low jet mass with respect to the Monte Carlo truth, while here, again, I forgot also to mention that the vacuum reference yields more or less the similar behavior as dual vacuum. That this is something that we are also aiming, right? We don't want to distort what we know, so we well, independently of the selection of the neural network, we want to make sure that the jets that we are recovering as identified as a vacuum-like are not distorted with respect to our PTA reference. And finally, we also looked for the jet radial profile, and we see that in Joule, okay, the kind of jets that we are selecting have indeed a profile that is somehow more flat. So we have here a point that goes right above the others, but the other ones is kind of flattish. But we have here some sort of structure that is very big and then suddenly some broader. So in a very, let's say, very extreme case, the medium light jet seems to be more collimated with respect to the Joule. And this is again, of course, expected because the jets in Joule, we know that the mechanism of Joule without medium recoils is to collimate the jets with respect to proton-proton. So if indeed the neural network is identifying jet quenching as the features that are included in the Joule Monte Carlo, in our Monte Carlo sample, this means that it indeed has to enhance features that we know that are already there. Now, of course, that all of them, when we look to the details, they all have differences. So all the neural networks will yield, of course, different results, but qualitatively, they all yield the same classes of jets. And this means that either jet images or Lund planes seems to deliver exactly the same kind of, let's say, jet classifier. What is the problem in this kind of approaches? Well, the problem is that different training samples will, of course, yield different selection of modified jets. And for instance, when we compare, for instance, to the work done by this group of people, we understand that exactly the medium light jets are indeed the jets that do contain more amount of medium response, because medium response is included in their samples, while in ours was not since the beginning. So the neural network cannot learn something that it's not there. And of course, this is the, but despite this, let's say, despite this, both neural networks actually identify medium-like jets as jets that lost more energy. But again, here the classification is not exactly the same because we looked for the jet asymmetry with respect to the boson, while in here they look for the same jet before and after going medium response. But in any case, qualitatively, we can say that medium-like jets are in the same way jets that lost more energy. But of course, that's the problem of this kind of deep neural networks, is that there is always this interesting dependence on the training sample. And on one side, if we feed the neural network with jet collimation, then this means that the neural network at the end of the day will enhance the population of jets that were collimated. While if the ingredients include, for instance, medium response, then the neural network will, of course, identify medium response as a crucial signature for identifying jets with quenching. And this, of course, it's one of the most difficulties when dealing with these deep learning techniques. And of course, it's a disadvantage of these, let's say, more brute force methods. Now, the other question is, okay, we already know how to work with this. We know what are the advantages, and we know we need how to think exactly how to overcome these difficulties. And I don't think that it will be very easy, or at least to me, it's not so trivial how to, or it's not so immediate to think how to solve exactly these problems. So why not, again, going to our old-fashioned jet substructure analysis that we have already some years of experience working with that. And so the other thing that we can do is to look for the jet substructure itself without resorting to this kind of deep learning techniques. And let's say that we look again to the jets and we try to understand exactly what are these jets. So jets from the point of view of operational. The definition is just a cluster of final state particles. We don't know anything about their origin or how do they cluster to the, or how do they get to the detector. We only grab the final state particles and we try to cluster them with a given recipe. And so we try we start clustering final state particles and again until we have this macrostructure that we call a jet. And this is nothing but just a hierarchical structure that we build from a user-defined recipe. And of course, if this user-defined recipe changes, this means that my overall structure of my jets will change. The jet itself can change, but more substantially, it will change his clustering history. And of course, that we are familiar with the generalized KT family, which is just cluster particles based on the transverse momentum and the distance in the rapidity and the azimuth angle space. And this generalized KT family, we are very familiar also with the anti-KT when this P equals to -1, that is the jet clustering that we use to actually tag jets in our events. But we can use also P equals to 1 or P equals to 0. And these two structures are very curious because they resemble more the angular, the QCD, let's say, basics of angular structure. In particular, the Cambridge-Aham is very useful because if we recluster jets with the Cambridge-Aham, and of course we need to apply soft drop because Cambridge-Aham is a completely geometric clustering algorithm. So this means that whatever we do, the last clustering will always be 1 at the edge of the jet, which might not be related to our to the hard fragmentation of my incoming particle that initiated the jet. And that means that I need to clean, let's say, from these soft contaminations. And usually this is accomplished by applying a soft drop procedure in which I'm just discarding branches that do not fulfill this condition. And when I apply this, I can nicely recover the expected behavior of the jet QCD splitting function. Now, the Cambridge-Aham is very nice because it really correlates the expected pattern that we get when calculating exactly the radiation pattern from a QCD antenna, for instance. We know that by calculating the interference between subsequent emitters, there is a nice cancellation between the radiation of these two in which we can retrieve this angular ordering component. This, of course, is at leading behavior, but at leading behavior, we know that these emissions happen always with smaller and smaller angles. And of course, when we look for the generalized KT family with P equals to 0, this is just geometry. And again, I start to cluster particles and also unclustering particles by this geometric distance, which again kindly is very similar to the angular ordering property that I have from vacuum QCD. But in the case of a medium, this is no longer strictly true because medium now, the interactions with the medium will destroy some of these interference effects between these two emitters, and a new component in addition to this angular ordering component will arise, and in fact, it actually follows exactly the opposite behavior. It's anti-angular ordering in the sense that the radiation now that is affected by the medium, so this delta met component now is a parameter that is related to the properties of the quark-gluon plasma, says that, okay, these kind of emissions that are affected by interactions with the medium will be emitted typically at large angles. And this means, and by the way, in addition to this, we also know that the fragmentation pattern of my jet will also control the final jet quenching effect. So this is again the jet selection bias that I was mentioning. And this means that if I have a jet that starts to spread and has a large opening angle in the beginning, my jet at the end will be strongly modified with respect to the proton-proton reference. While if I have a jet that is very thin, very collinear, this means that will not be modified by the medium. So this term here will be almost negligible, and my hard structure of the part and shower will basically follow kind of vacuum-like behavior, and in the end I will have a weakly modified jet. So our question was, okay, and given this setup, even we wondered just that perhaps Cambridge-Graham would not be, again, the best algorithm for studying, in this case, jet substructure in the presence of a medium, because my emissions will now not follow, strictly speaking, angular ordering. And that's why we tried a different algorithm, which in this case was set equals to p equals 0.5. And the reason for this is because at the end, you will end up with something that is proportional to the inverse of the formation time of your particle. And the formation time, of course, is just the invariant mass, the inverse of the invariant mass, boosted by the energy of the particle. And when you look at it at its definition, of course, this is a parametric estimate, but one thing is we notice is that it has somehow a dependence with the angle. It still keeps track of the geometric distance between the particles, but now it also waits for the PT. And so it's something between the KT and the Cambridge-Graham. And so we tried to actually try this method. And we tried, of course, with PT, just to understand if the vacuum reference at least can work there. And we tried with our Monte Carlo, that in this case is Joule, of course, in Joule vacuum and Joule medium. And this has the advantage also to understand exactly if this correlation holds independently of the kind of part and shower ordering that I have there. So, for instance, PT8 is based on a KT ordered shower, but Joule, because its base is a modification of PT6, its core part and shower is actually virtuality ordered. And in medium, we still do not have exactly the anti-angular ordering component implemented in the Monte Carlo, but we have something that's more or less is similar or tries to resemble a bit, that is a veto in terms of formation time. So the Joule is always trying to test, let's say, medium-like emissions, and the ones that have smaller formation times are the ones that are realized. And so we have a part and shower that is given by our Monte Carlo, and we have our jet. And now the question is, if I have a part and shower developing on top on some medium that is evolving, this means that if the scale at which this emission occurs carries information of the medium information, it means that carries information of the local intensity of the medium at this point. And the same for here and the same for here. So if I have a medium that is diluting with time, I have splittings that actually carry information of this dilution. And so if I look now for the clustering tree of my jets, I can hopefully identify exactly, again, this kind of scales that are related to the scales of the quark-gluon plasma. So if I have a scale that is related to the quark-gluon plasma, then I have something that perhaps can tell me if my jet is being strongly or weakly quenched. And of course, for the part and showers, all these questions, if it's KT or virtuality ordered, at leading log accuracy, they are all equivalent. Of course, that in the practice, we know that there are violations to these leading log behaviors, and this is where the difference between all the Monte Carlos will arise. But hopefully, hopefully at the end, what we will have is some sort of, instead of angular ordering behavior as in vacuum, we have something that is ordering in some sort of QGP related scales. And our hope is that this QGP related scale is the formation time. And so what we did to try to understand if this is in fact something useful was just to make a sort of bridge between what the part and shower is calculating, we get for the formation time from the part and shower, and what we can calculate using only jet information. And we use this as a measure of our correlation when doing this unclustering tree with this algorithm that we call the tau. And of course, hopefully all these emissions will match, but sometimes it may happen that they will not match. And when this is the case, we will have an incorrect correlation between these two. So this is the plots for the correlation. This is the formation time that we obtain when using unclustering information. This is the formation time that we do, that we get when using part and shower information. This is just for PITIA, okay, pure vacuum. This is for Cambridge-Aham, and this is for tau algorithm, without any kind of soft drop. And as you can see, without soft drop, the Cambridge-Aham, of course, the correlation is very poor because the first emission is something that is just at the border of my jet, so it's not related to the jet in any way. While for the tau clustering, I have here some positive correlations, but I also have here a very large amount of emissions that are just mismatch between the part and shower and the clustering sequence. But fortunately, we know that even for soft drop measurements for the jet splitting function, we do need to use grooming, and there's no other way we need to clean the background contamination and the background particles that are coming just from soft radiation. And when we do that, we apply soft drop to clean exactly these soft large angle emissions. We now end up with something that is much more better behaved in both tree of the algorithms. Now, to classify, in order to actually quantify what is the improvement that we are getting when using this tau clustering tree instead of the usual Cambridge-Aham, we just look for the difference between the information of the formation time given by the part and shower and the one obtained from the clustering. And as you can see, of course, this distribution is highly peaked at 0, which is nice. These are all the events in which we know for sure that they are nicely correlated to the part and shower. The other ones are just mismatches. And so, because it's really steeply falling distribution, we cannot actually quantify statistically this distribution very meaningful. So we just use the quartiles informations as some sort of quantitative measurement of the distribution. And we see here that we have the quartile, the median here in the zoom, in this panel, and we have here the Q1 and Q3 as asymmetric error bars to give the measurement of the interquartile range. Of course, we are aiming for something that gives us very central median and shorter interquartile range. And we see here the first, second, and all emissions across the leading part and the leading branch of my part and shower, and overall, the tau algorithm in vacuum always show a better performance with respect to the remaining P exponents that one could play in this generalized KT algorithm. Okay, so now that we have our let's say proxy for the formation time, let's see what we could select out of it. And the first thing we did was to look exactly for the available timescales that we can withdraw with this formation time. And this is the distribution that we have. So at blue is the one in which we recover the formation time out of the dual vacuum, and at green at dual medium. And of course, here we see already again some sort of selection bias in which we are again selecting jets that have, of course, a harder fragmentation. If they have a harder fragmentation, they will have a longer formation time. This is the peak structure that I see here. So these jets, of course, will tend to survive more in our selection, and we end up with this distribution here. Now, even with this distribution, now we can kind of select two classes of jets, right? The ones that we say we classify as being early, and these should be the ones that will be strongly modified because they have a formation time that happened very early in the medium, and the ones that have a late formation time. And this would what we call the late jets. And we just use these numbers as just proxies, just to have a very kind of homogeneous distribution in this log scale distribution. And as you can see here at black, this is DRA of the leading jets. Of course, that the results, all the results that I used were tested for, again, Z plus jets, but with the PT above 300. And of course, here we are extrapolating now to lower and lower momentum, but the resolution, of course, will deteriorate with smaller transverse momentum. And as you can see here, at solid, we have what we identify as being strongly, at solid, what we identify as being weakly modified, which is the late jets, and that dash the early jets. For reference here at black is just the reference from the Monte Carlo sample. And here in solid, we have green, the Monte Carlo truth, and orange and purple, the ones obtained with Cambridge-Aham trees and Tau recluster trees. And as you can see, despite the differences between them, we see that indeed Tau seems to always perform better and correlate better with the Monte Carlo true. Cambridge-Aham seems to yield constantly slightly more quenched jets than the Monte Carlo truth. But one thing is for sure, is that using this metric, we can indeed select jets that were strongly modified, as with that we labeled just as being early, and jets that were weakly modified and that we labeled as being late jets. And this works equally well, depending if we have recoils or not in dual. Now, this of course can be used as a jet classifier. So I just recluster my jets, I measure the formation time, and I use this as telling me if the jet was in fact strongly or weakly modified with respect to our proton-proton reference. But never, there are no free lunches. And of course, one problem of this variable is its interpretation, because we want this kind of formation time gives us, or we were hoping that this could give us information on the time structure of the jets, and with that, the time structure of the quark gluon plasma. But it's not very clear if it's just a correlation with the jet structure, that is the opening angle of the jet. If my jet again is very collimated, this means that it will survive more to the medium. And this, of course, will have a larger formation time, or if indeed this gives a notion of the time that the jet spends, let's say, inside of the medium. But regardless, I think we can say that the formation time can indeed be used also as a jet quenching classifier. So as a summary, I think that the identification of these classes of jets quenched and strongly quenched and weakly quenched can really help us to understand exactly what's going on, even more in the light systems, because if we understand clearly what is happening in the more strongly cases, we can perhaps try to constrain more our models and reduce the uncertainties when extrapolating now to weakly quenched scenarios. And for that, we need a jet quenching classifier. Of course, we can use brute force methods like deep learning techniques that without a heavier environment, they in fact seems to be quite consistent independently if I use jet images that are more subject to the background contamination, or if I use lone planes that are a little bit more resilient to this kind of things. But of course, there's always an issue of the training sample, and the training sample will of course affect our selection criteria. But this is always something that is connected to this kind of methods. The other is to return again to our jet substructure measurements, in which we already have some handle and some knowledge also from proton-proton collisions. And we try exactly to use some sort of metric that somehow weights the angle with the energy of the jet, in this case, the formation time, to actually identify these two classes of jets. And with that, again, try to understand more about these jet quenching effects. And with that, I finish the talk. So thank you very much for your attention.
All right, great. Thank you for the very nice talk. Do we have any questions from the audience? Yes, I see Isabel has her hand up. Go ahead.
Hi, Liliana.
Hi.
Thank you very much for this talk. I have seen parts of it before, but I'm very intrigued by this tau form, this tau form method of classification. I'm just a little bit trying to understand this plot on, I think it was slide 33, to try and understand. I'm trying to understand this plot on the left-hand side. I sort of thought, okay, so in my mind, I would have thought that the mean free path in, say, in this lead, so for the green curve, the mean free path would be around a tau form of, say, 1 Fermi, right? So around 0. Is that's something I should have in mind? I'm wondering why this peak structure is so far. It's sort of almost at 2 or at 1. So that looks like a peak sitting at 10 Fermi. Is that correct? So you're saying that the majority of the splittings in this green curve, in this lead version, the majority of the splittings are happening with a formation time of, I don't know, 10 Fermi or 20 Fermi?
Well, this peak structure is a little bit dubious, right? Because this is the distribution in linear scale. And I mean, it has a long tail, and that's one of the problems. That's what, so this peak is in fact the tail of the distribution. And so it's true that half of your sample, it's above this 1 Fermi. It's not that they are, so you cannot see this peak because this is all condensed. So it's basically the scale all condensed suddenly in that peak because we use the log scale. But you don't have the peak structure. You have just a very broad tail here in this part.
And the point is that the tail becomes broader in lead than it is in vacuum.
Yeah, exactly.
All right. Okay,
yeah.
Cool.
And this tail, of course, appears because we have, well, I don't know why this, okay. Because we have this cut here that is 300 GeV. So we,
I see.
At the end, you are always selecting jets that had indeed experienced less energy loss effects.
And I guess I see you have a very broad R there as well. They're also at 0.5. Okay, fantastic. Okay, thank you very much.
Great. So James had a question next.
Hey Liliana, thanks for the very nice talk. I had a question actually on your next slide, 34. And I think you had some like question that came up. Maybe if you go forward again. Right. So I thought this was like very nicely phrased question of like, how should we think about this formation time? Like, should we think about it in a way that is like purely, a different observable to classify jets by, or is there some way we can like in a deep kind of theoretical way connect to the question of the jet going through the plasma? So I kind of just wanted to like ask your opinion on the prospects for this. Like, do you view the formation time more as just, so to speak, another or maybe an efficient way to classify jets, or do you think there is like a theoretical path to actually answer the question of like how much is the jet actually going through the plasma and being modified according to like some notion of time? Yeah.
So what of course we were aiming for was the second, that we could in fact relate this formation time to this notion of I can use this time as exactly to correlate with the time that the jet spends inside of the medium. But the more I think of it, I'm not so sure, because the formation time is just a consequence of your kinematics. And the kinematics that you extract is just a consequence of your vacuum kinematics. But if you think of medium-induced radiation, actually formation time goes opposite with the energy, not the same way as in the vacuum. So in the vacuum, for instance, soft gluons are emitted later, while hard structures are emitted sooner. While in the medium, it's the opposite. So soft radiation is emitted very, 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 very fast. of course, that the problem afterwards is if this radiation is in fact included, or if it's captured inside of your jets. And if it's captured inside of your jets, if it passes afterwards the soft drop grooming. So if, and this is a lot of ifs, I think, if you are triggering in just on hard structures, at the end, I think you could relate this with the formation time, and with the time in which you could use hypothetically to actually try to think of these space-time pictures. But otherwise, I think it's just a more efficient, and I say efficient because you do need to wait also for the energy. So only in angle, I'm not so sure if it will be so much more efficient to actually trigger wide angle versus small angle radiation on something that is related to strong quenched and weakly quenched jets. So, but I don't think that the answer will be so straightforward, at least in the next, for me personally, it will not be so straightforward to answer.
Mm-hmm. Okay, thank you.
All right, so Kyle was the next question.
Hi, can I actually ask a very basic question? You talked about formation time computed using parton shower and jet clustering. Can you repeat the procedure, how you determine for these two definitions again?
So the definition is always the same, is this one. It's just the boost applied to the mass with the limit of massless particles, because otherwise it will be a mess to calculate this in the parton shower. In the clustering, you could hypothetically take into account the mass as well. For photons, it doesn't really matter, but at least to correct this for pions. But the prescription is always this one. It's just the fact that we use the information of the parton shower for the energy and the fraction and the angle, or the information that we retrieve from the clustering. But again, we take into account the energy of the clustering of the subjects.
But these clustering history you generated also using Monte Carlo, or?
Yeah, so yeah, we simulate the jets, and then we just apply the algorithm to the final list of particles, and we retrieve the information from the end clustering.
I see. And what does the off-diagonal piece teach you again? Like the fact that they actually differ?
So this is just the emissions that happen actually in the parton shower. So when we go through the parton shower, the first emissions will not be captured inside my jet because my jet has a radius of 0.5.
Mm-hmm.
So if, for instance, another way to minimize this would be, of course, to increase the radius. And if I increase the radius, these emissions will be captured inside the jet. Yeah.
Okay, thank you.
Okay, so Wei Yao has a question next.
Oh, hello. Hi. Thanks for the talk. Just some comments still on the formation time. I think the formation time that we constructed from the kinematics is, if we map it back to the kinematics of the partons, still measures the time that these partons lose like interference with each other. So it's not necessarily the time that we try to measure at which point inside the quark gluon plasma that this splitting happens, right?
Yeah, that's still another, yeah.
If you plot the formation time distributions, a lot of them are actually happen far away outside of the medium. But I think it's still useful because if you not focus on the vacuum shower, but the medium-induced part, in that case, it's because of the particular splitting structure of the medium-induced contributions. Most of these splittings are actually going to happen within the medium, with the tau within the medium, very soft emissions. So I wonder if, for example, on this histogram, if you also overlay it with the distribution of the path length, like how much of this formation time will actually fall within the medium, so that we can be pretty sure that even this thing is constructed with the kinematics, they still have to form very early inside the medium.
Yeah, so these numbers were chosen not only to sample our distribution here, but also these numbers correspond exactly more or less. So the Bjorken model that is implemented within Joule, it falls below the critical temperature for the hydrogenization at around 5 Fermi.
Oh, I see. Okay, it's a Bjorken model. Okay.
Yeah, for this Bjorken, yeah. But this is a very simple model. Yeah. So considering only the numbers that we selected and considering the length of the limit that's implemented within Joule for this setup that we used, we would expect that these jets to be roughly unquenched, if this was to be interpreted as the formation time of the first splitting.
Mm-hmm.
But again, this doesn't discard the fact that this might just be a consequence of selecting narrow jets that probabilistically didn't experience, again, any kind of interaction with the medium. So I think here is just, that's my problem with the interpretation, is just what is the cause and consequence. So the fact that we see the correlation doesn't mean that there is there will be the cause consequence that we were expecting. But I think it will be difficult still to understand if.
Okay, thank you. Oh, sorry.
All right, Matthias, you have a question?
Yes, hi. Hi, Liliana. Nice to see you,
Hi.
by the way, and very nice talk. So good food for thought, first of all. Now, I waited a little bit with my question because I was thinking about this, but let me say about the comments on the machine learning efforts. We are actively working on let's say a approach that would finally give us some attack on the data. So my comments are essentially that, in paper by Conrad et al., there's not even a mentioning of background, right? In your paper, the word background appears twice, and you properly recognize that you actually ignore the issue. And when I mean background, I mean particles not associated to the jet that you want to study, etc. Right? And there's lots of this stuff in heavy ion events, and actually central. And you actually mentioned this, that if you try it, you're going to have a very bizarre answers, actually, or it's going to be difficult. So you have to be careful about the procedure and your observable that you want to study. And there's been also efforts to elucidate that. And the second comment is model dependence. I know we have, Joule. We also have other quenching models like QPIT. I would be really interested in what the machine learns from QPIT, which essentially doesn't narrow but broadens the jet. I mean, depending on how you turn the knob. And my personal understanding is how the machine or those models work. It would essentially prescribe, or let's say find a minimum that modified jets are those ones that are widened, right? That you'd be completely opposite to the statement of Joule, because for Joule, the same model would tell you that the modified jets are the ones that are narrowed. So what do you do with the data in that case? So this model, I mean, I'm trying to illustrate it in the strongest possible way. It's difficult. So we need to go into some data-driven type of data-driven or model-independent machine learning. Let's put it this way, which is indeed difficult. So machine learning is as good as your training data. That's what I think we should always remember. Mm-hmm. Yeah, but it's very interesting effort. So to my question, sorry, it's about tau. How? I'm sorry. So how much this clustering sequence with the p of half is different from p of 1, essentially with the standard KT algorithm, did you try to see sort of jet by jet and splitting by splitting where the decision on reclustering actually differs? Because I think, so I was thinking about this for a moment, it cannot be that different. You know, in one case, you just take the PT to the power 1, or in another, you say PT squared when you minimize Dij. I think most of the splits that you actually get with the tau of half will be very similar, if not the same, as compared to KT algorithm. The differences might be in those first splittings, okay? When you already mentioned this, if you take the first splitting, it's probably some happening. I mean, it's like last reclustering. It's probably somewhere on the edge of your circle. Let's put it this way, of your radius, right? That's the last one that gets clustered. But all the rest, I assume, especially in this, let's call it perturbative region, might be just the same. So it would be good, or maybe you tried it already, to see, you know, splitting by splitting to see where these things differ.
So
just a thought.
Yeah, not
and for the groomed, probably it would be the same. But anyway.
Yeah, so not in the way that we checked jet by jet, but we checked the overall, let's say, correlation that we got when using KT. And the problem with KT is that it's always yielding larger formation, smaller formation times with respect to the Barton shower.
That's on average, isn't it?
Yeah.
You're talking about on average. Now, my question is, what happens if you throw away the soft stuff that probably where KT gets a little bit more sensitive to?
No, this is already with subtrop.
Oh, with some, okay.
Yeah, all these 3 curves here are for KT. This here, and as you can see from the orange, I have here always this shift in to the left, to the right. While the P equals to 0.5, it's almost none. And
I have to digest this figure again, but it's like it almost tells me how the distribution looks like for different P exponent. I see.
Yeah. So for the first emission, on average, they all more or less.
Tails, basically. Mm-hmm.
Yeah. So on average, they almost for the median, they more or less behave the same. And this, in fact, we see, for instance, for the selection of the strongly modified jets, in which we don't see significant difference between the Cambridge-Aham or the tau. But for the tails of the distribution, this starts to matter. And for the tails of the distribution, we see here, in fact, this is where the deviations from all the P starts to appear. So I have, for instance, Cambridge-Aham always, for instance, yielding formation times different from the Monte Carlo true in the same way as, so up in the opposite actually direction with respect, for instance, with KT. And I think that when we actually looked at this figure, I was very puzzled to see, I mean, why is P equals to 0? The 5 so good. And I think it's just the question of the metric. So we are, in a way, using the metric itself that the jet algorithm is using. So if we want to retrieve formation time, it's better to use an algorithm that uses formation time as metric to cluster particles.
Okay, good food for thought. Thank you very much. Thanks for your answer. And thanks for the talk.
All right, we've had a lot of great discussion here. So I think we'll wrap up at this point. So thank you very much, Liliana.
Thank you very much.
Yes, and for everyone else, we'll see you next time.